Alright, so here we have a bunch of resistors and they're arranged in a sort of Pascal's triangle looking scenario. And what we want to do is find the effective resistance of if we reduced all of this down to a single resistor. So if we had a current coming in here, we'd have the same current coming out over here by Kirchhoff's first law. And so we just want to find the resistance of all of these put together. So how can we do that? Well, let's start off by reducing each of these resistors in parallel into a single resistor so that we can get something that looks like this. So if we can get a chain of resistors like this, then we know we can just sum them up using resistors in series. So okay, for each parallel branch, let's just start on this one, and I'll call each branch R0, so we'll just go up like so, and obviously R0 is 1 because there's only one resistor there. We're going to have to use the formula when in parallel. The formula for summing resistances is this here, where R1, R2 are the resistors on the individual branches. So we can see, and what I'll do is just rearrange this for RT by reciprocating each side. Okay, so we can see R1 is going to be, well, this is just going to be 1 over 1 plus 1 over 1 to the minus 1. And this is just going to be 1/2, because this inside is 2, and that's 1 over 2. Then R2, this is going to be 1 over 1 plus 1 over 1/2 plus 1 over 1. And so if we reduce this down, we get 1 plus 2 plus 1 to the minus 1, which is going to be 1 over 4. R3 is, this is going to be 1 over 1 plus 1 over 1/3 plus 1 over 1/3 plus 1 over 1, all to the minus 1. And again, reducing this down, we get 1 over 8. Okay, so hopefully you can see what's happening here. We seem to be getting the reciprocals of the powers of 2. And why is that happening? Well, you can see for any R, we're just going to have, it's pretty clear that this is going to end up being Pascal's triangle. This was 1 plus 1, this was 1 plus 2 plus 1, 1 plus 3 plus 1. Because of the way these resistors are arranged, when we take the reciprocals, we end up with the numbers in Pascal's triangle. And what's interesting about the numbers in Pascal's triangle is that every row adds up to a power of 2. I think there's a proof for this, but yeah, you can look this up, and it's something to do with how the combinatorics, so this would be row 0, row 1, row 2, row 3, row 4, and row 5, something to do with the combinatorics. So let's say we summed up row 3, we had 3 choose 0 plus 3 choose 1 plus 3 choose 2 plus 3 choose 3, because remember, Pascal's triangle is another way of calculating the choose function, because every single item sort of represents a number of paths to get to that, so the number of choices that had to be made. For example, to get to this one would be 3 choose 2. And yeah, the identity is something like this, where if we sum these up, that's equal to 2 to the 3. But yeah, using that identity, we can now say R of n is going to be, well, it's going to be 2 to the n to the minus 1, because we haven't accounted for that yet, so that's just going to be 2 to the minus n, or 1 over 2 to the n. So now we can simplify down our circuit into a bunch of series resistors, where each resistor has a power of 2 resistance, like so. Now to work out the overall resistance, we can just use the series summing tactic, easier one, and this is just going to give us a geometric sequence. And so we'll just use our formula, a over 1 minus r, where r is 1/2, a over 1 minus 1/2 is Same thing as 1 over 1/2, which is 2. So there's our final answer. This entire Pascal's triangle resistance sort of scenario has a overall resistance of 2 ohms. Pretty surprising, but also makes sense when you do the calculations. Thanks for watching, and I'll see you guys in a future video. Bye.